Hello, everyone. Today we're going to be talking about securing Arm MCUs for IoT applications. My name is Timothy Stopko. I'm a senior software engineer at Microsoft. For a little background and introduction, I'm the security lead for Azure RTOS, formerly of ThreadX, which was acquired with the ExpressLogic acquisition a couple of years ago. I have 20 years of experience in embedded development with an emphasis on security, and I'm the architect and lead developer of the Azure RTOS TLS stack. Sort of the impetus for this talk today is the Internet of Things grows. It's increasingly pushing into the MCU space. More devices connected means that there's more data to analyze in the cloud, which presents a whole host of new opportunities for business. Unfortunately, connecting microcontrollers to the cloud comes with an inherent risk, since traditionally they've not been designed with security in mind, even if they have connectivity. There's some unique requirements of microcontrollers. I mean, there are many trade-offs to consider. The cost of security hardware is significant in the MCU space, and are we trading some of that security for cost or performance? The application space that you're working in, either consumer or industrial, can make a big difference. And then even at the lowest levels, talking about what type of operating system you're doing. Do you need a real-time operating system or something a little more full-featured like Linux? So to start out, what do we mean by an IoT microcontroller device? Typically, we're talking about resource-constrained devices with less than 2 megabytes of flash, half a megabyte of RAM, typically off-the-shelf silicon, inexpensive and low power. We're typically talking about RTOS or bare metal applications. And some of these devices may have limited connectivity, capable of just 1 or 2 network connections via Wi-Fi or cellular. Others still may have more capability. The security model is pretty much the same for all of those. One of the big points that is a big issue in the microcontroller space is that security has often been, and still frequently is, an afterthought. And this is a big problem for connecting large numbers of IoT devices to the cloud, because without some form of security, there are things like the Mirai botnet that show that even a small number of connected devices can have a major impact on businesses and the economy. So that being said, platform choice at your design time is critical to building a secure application. It is possible to add security to existing devices, but that's really outside the scope of this presentation. We're looking at building new microcontroller applications with security from the beginning. So just a brief background on security. There are basically 3 pillars of information security: confidentiality, integrity, and availability. Confidentiality is protecting information from being stolen. That's going to be your encryption to prevent prying eyes from seeing your secret data. Integrity is assuring that the information isn't tampered with or corrupted in transit. And availability is assuring that information is available when it's needed. And so these are sort of the background of security that we'll be sort of talking about in the context of microcontrollers. Thankfully, or not thankfully, depending on your view, there are a number of different standards and certifications that exist to codify the security principles into somewhat usable guidelines. The one we're going to be talking about today is Arm PSA Certified, but there are a number of others here: Common Criteria, SASIP, the IoT Security Maturity Model, ISO, and FIPS. There are certainly others out there that are in various stages, and all of those are sort of a useful reference for building secure applications. And depending on your industry and target market, some of those may be more useful than others. Before we talk about anything security, we have to talk about hardware. Without proper hardware, there's little to no security. Software by itself cannot provide any security, so we're going to have to rely on hardware. The protection of data really cannot be done completely in software. And one thing to note here is that information security is separate from device security. If you encrypt all of your communications, which is a software operation, but your device is compromised and somebody grabs your key, your encryption is useless. So without some kind of proper device security, you're going to be in trouble. Unfortunately, there are a bewildering number of options. And one of the biggest challenges in selecting hardware is choosing what features are needed. And unfortunately, there's no clear answer, but all of the security principles and standards that we mentioned can help guide your design decisions, as well as you know your cost and market needs. And we're going to talk about PSA Certified, and it provides a good starting point for your ARM-based microcontroller designs, because it provides sort of a pretty good overview of what makes a secure microcontroller. Speaking of connecting to the cloud, TLS is the sort of de facto standard security protocol for most of the internet, regardless of your connectivity or platform choice. You need that end-to-end security, and the TLS forms the backbone of IoT connection security. All of the different cloud services do everything over TLS. TLS is a transport layer security. It's a framework that allows you to specify specific encryption operations that are then used to exchange secret keys that are used to encrypt your data. It also includes authentication for your device, so that you know that the device is talking to the proper server and that the server is talking to the proper device. Currently, TLS 1.2 is the standard for IoT. TLS 1.3 is a much newer standard. It's only a couple of years old. It is available, and it's in the early stages of adoption, and should be taking over in the next couple of years. X509 authentication using digital certificates provides the best solution for connectivity, security, and authentication. There are other options available, but for the most part, any type of IoT device, except for some of the very smallest and most resource constrained, you're going to want to use some form of digital certificate, and X509 is accepted pretty much everywhere. TLS, as I said, is that end-to-end security. It provides the confidentiality and integrity that we talked about, those security pillars. One thing to note about TLS is that it's only as good as the cryptography that you give it. Since it is a framework for using cryptography and not defining the cryptography itself, you need to be sure that you're using up-to-date algorithms that are accepted by standards bodies like NIST, and making sure that you are using proper key sizes, because even a good algorithm with too small of a key, it could be a problem. And in general, software cryptography is just fine, but in many cases, hardware cryptography is better. It's going to be faster. It's going to take less memory on your device. There are some caveats to that, so you have to be careful and make sure that your hardware actually supplies the algorithms that you need, especially looking forward towards future updates. But generally speaking, you're going to have a little bit better time working with hardware-based cryptography. So as more and more MCU devices are released with built-in security, which has been a little slow in coming in the industry, but we're seeing it pick up pretty rapidly with IoT. We have a whole bunch of different options. And the one we're going to be talking about today, of course, is the Arm TrustZone, which is available on select platforms like the Cortex-M 33. Some vendors supply on-chip hardware cryptography with proprietary APIs or PKCS11, or tied into TFM, which is another thing we're going to be talking about today. That's an implementation, a reference implementation of Arm's PSA security spec. The PSA functional APIs are implemented in TFM, and that's going to be a sort of an important part of the PSA certified security fundamentals that we'll be talking about. Another thing to note is that HSM's hardware security modules, also called secure elements, these are discrete devices that can be paired with MCUs to provide hardware-based security. HSMs are great for being able to provide a hardware root of trust, which is sort of the best form of trust that you can provide on a device. There are other ways of doing it, but having a secure element that is dedicated to that operation is going to be your best bet for the highest level of security. HSM secure elements store keys and perform cryptographic operations on those keys. And one of the key points of an HSM is that the key itself, the private keys, never have to leave the device. They can't be read by an application. They can't be read by malicious code. And any operations that you're going to perform using that key are done through the HSM interface, and that key never has to leave the secure internals of that silicon. So if you're looking for the highest level of security for your microcontroller application, HSM secure element is the way to go. However, if you don't have the budget to add an HSM, if you have TrustZone and TFM together, there are ways of implementing that root of trust without the secure element, because TFM provides services and interfaces that satisfy some of the requirements for things like hardware-based root of trust that we'll be talking about in a little bit. So now that we've sort of covered the basics of security in the microcontroller world, we'll get into the meat of the talk today, and that's the PSA Certified process and certification. All PSA certified devices are required to cover these 10 security goals. There's a certification process by which you submit your device design for review to a laboratory. The laboratory then will evaluate your application and do some testing and provide you certification of your device. PSA Certified offers 3 different levels of certification with increasing levels of robustness and security. You can look at the PSA Certified website for a little more information on what those levels are. But we're going to be talking about how we can meet all of these principles and goals with an RTOS-based microcontroller application. So the 10 security goals of PSA serve as a checklist and provides developers with an idea, some foundation for building secure applications based on ARM microcontrollers. The aim of these goals is to cover a wide range of possible vulnerabilities and with some specific mitigations for different types of exploits that have been seen in the past. We're going to be looking at the goals, as I said, in terms of an ARM Cortex-M33 device running RTOS application that connects to Microsoft Azure. This is definitely not a comprehensive analysis. Introduction to some technologies that are used to support is really just an introduction to some of the technologies that are used to support PSA Certified and the goals there. So each PSA Certified IoT device must have a unique identification. Unique ID can be something as simple as a large random number. As long as it's globally unique to that device, it can serve as an ID. In practice, however, the unique ID is something that has properties that allow it to be used for attestation, which is just to verify that the device is valid and belongs to a particular group defined by the owner. So you can see if the device has been revoked or compromised or something else. And typically the way it's implemented in practice is through the use of an X509 certificate, typically with a hardware protected key that is burned into the device. You could use an HSM. You could use something protected in the TFM TrustZone protected memory. As long as that key is unique and can't be forged or compromised easily, it can be used as that unique identifier. All PSA certified IoT devices must support the notion of a security life cycle. In our RTOS example, the security life cycle is done through monitoring and logging, and also secure boot and firmware update. Part of that life cycle is tracking the device from manufacturing through deployment using that unique ID, which can be used to identify that device from the moment it's manufactured until it is disabled and goes end of life. Auditing and logging facilities allow for the gathering of device status, and that information can be fed to the cloud. There's Azure Defender is a service provided by Azure that allows for cloud services to collect information and detect any kind of problems in devices, hopefully before any problems spread. It can detect errors, it can detect possible exploits and possible attacks. Monitoring services such as those provided by TFM provide status information about the physical device, and TFM itself has the notion of secure faults that cause the device to go into a lockdown state, depending on the application configuration and what the physical monitoring is actually looking for. We briefly mentioned attestation with the device ID before. All PSA certified devices must be able to provide attestation information for independent device verification. Essentially, this means that the device can be called upon at any time by the cloud services to provide status information, and then using that unique ID and some cryptography, the device can be verified, and the status that's being reported can be verified. And it's important to note that being able to verify the data that's coming from your devices is going to be important because an attacker may want to create fraudulent data to trigger a security problem that doesn't exist. So it's important to have that unique ID and the cryptography behind it to authenticate the information that you're collecting. Secure boot. Secure boot is the process of the device checking to make sure that only authorized software and firmware is running on the device. Typically, secure boot mechanisms measure the firmware somehow using a small bit of highly trusted immutable logic that's built into the hardware. It measures the firmware, typically some kind of hash, and before actually executing the application. It may also measure device state to see that the device itself is uncompromised before booting a firmware image. Secure boot is typically provided by the MCU vendor, and some support is based within TFM, but a lot of solutions rely on the open source MCU boot, which is open source secure boot implementation. It's important to note that secure boot and firmware update or over-the-air update are aware of one another, because when you update the firmware image, the secure boot measurements also need to be updated, or you will have boot failures, which is a problem. Secure update. So sort of in tandem with secure boot, only authenticated and legitimate firmware images should be loaded onto a PSA certified device. So this is the other half of the secure boot story, where we want to be able to change the information, the application running on the device, and so we have to be able to get the image to the device. That's the delivery part of the equation, and that requires some kind of authentication. The device needs to know that the image that it's about to load is valid and actual trusted firmware. The other part is firmware image encryption, And so that's actually to protect the image in transit for intellectual property reasons or privacy reasons. Um, and so those two together form the over-the-air update or secure firmware update story. Delivery should be authenticated with a signature. That's a combination of a hash and a public key encryption operation. Um, and there's a number of different options for device updates. Device update for IoT Hub, which is part of Azure, sends the image and hash over a protected channel, but downloads the image itself over a plaintext HTTP, and encryption is separate. So depending on your application needs, there are some different options there. Anti-rollback is a goal that assures that PSA certified IoT devices cannot be rolled back to an older firmware version that may have vulnerabilities. So in the process of updating to a new firmware image version, it's very likely that an older version may have a vulnerability, and that would be the reason to update the firmware. And so it's critically important that an attacker can't roll back the firmware to an old version. And so that mechanism needs to be built into the secure boot logic, and should probably be enforced at different levels. So tracking at the cloud level, the whoever's in charge of distributing images can track it before the images are even pushed to devices. It can be tracked at the application firmware update level. The application itself can check and verify that the version is correct and isn't an older, possibly compromised version. And then at the trusted computing level within TFM or the secure boot mechanism, that can also be used to track and protect against unauthorized rollbacks. Isolation. Isolation is a goal of separating services within a microcontroller device using hopefully hardware. Without some type of hardware isolation mechanism like TrustZone, there is very little that can be done to protect a wayward application from being able to access memory it shouldn't otherwise be able to access. The isolation concept is designed to protect secrets and sensitive data from any kind of compromised application code. In security, we assume that any bit of code will be possibly compromised at some point, so we need to put walls up between those different pieces. TrustZone itself is fundamentally an isolation technology, which divides the firmware into trusted and untrusted partitions, and has strict limits on the interaction between those partitions. TFM builds on top of TrustZone to provide an interface and a number of trusted services such as cryptography, protected storage that can be accessed from the non-secure side, but in a secure way. Interaction. So this is the other part of isolation. Interaction is the idea that the interfaces between those isolated services they have to be properly designed to prevent any kind of compromise across the boundaries. If you have your processes and services separated and protected by hardware isolation technologies, but your APIs allow anybody to call in and do critical application things like encryption and decryption, you're not actually providing much security. But fortunately, the TFM PSA functional APIs provide a programming model and a number of features that promote the isolation, but still allowing those services to be used from the non-secure application side. It's a connection-oriented protocol is difficult, and it's much better to use a standardized interface or implementation such as TFM or PKCS 11. Secure storage. All PSA certified IoT devices must have a way to protect sensitive data and secrets. Secure storage may take the form of encrypted data in non-secure memory. This is typically done with something like what they call a wrapping key. It's a key that's generated in the secure cryptography services or an HSM device, and the data is stored in unprotected memory, but it's stored in an encrypted format, and it's decrypted with that same key whenever it's used. So data being stored on the device in that way is as safe as the key stored in the HSM or within hardware somewhere. TFM with TrustZone provides a protected storage service, which can be used to store sensitive application data directly. Or, like I said, you can generate wrapping keys to store data in just a normal memory location. And it's also good to note that HSMs do sometimes feature limited storage capacity, usually for keys or small bits of data like certificates. And that's fully isolated from the MCU as well, which is good. And we would be remiss if we did not talk about cryptography in a security talk. And so one of the most important aspects of any secure device is cryptography. And all PSA certified devices must have a limited set of trusted services for managing secrets and keys and providing cryptographic functionality. TrustZone provides the isolation part, and TFM provides the interfaces and the implementations of cryptography that can be used via the TFM PSA APIs. Internally, the TFM secure side cryptography may be tied into hardware support or even potentially an HSM secure element device to provide that trusted computing base for your application. HSM provides an equivalent or better set of trusted cryptography services with that additional physical isolation because it is a discrete component. And that provides an additional layer of protection from the unsecured application code. But if you're using TFM to protect the X509 private key and perform cryptographic operations, you can be sure that that key is protected and isolated by a TrustZone when you're using TLS operations, such as when connecting to Azure IoT Hub. So in conclusion, this was a brief intro to PSA Certified and RTOS microcontroller application security. Microcontroller-based IoT applications are a growing segment of industry, and there's a lot of growing pains right now as we're building out a lot of the services and applications to take advantage of these new technologies. And one of the big issues is we have a big problem with security in the microcontroller industry. According to the SES-IP people, only 4% of deployed IoT products currently have security. So there's a lot of work to be done to solve that problem and prevent potentially catastrophic attacks in the future. And it's important to remember that microcontroller and RTOS developers are generally not security experts. They're experts in embedded development and haven't traditionally focused as much on the security side. So watch out for industry standardization. There's a lot of efforts underway to help guide IoT microcontroller application development in terms of security. So there's a lot of good things coming, but it's important to remember security as a critical part of any IoT design. And that's it for today. Thank you for listening.